Good morning, students. Today in magnetic materials, we will see the classification of magnetic materials. I am Dr. R. Priya, Professor of Physics, RMD Engineering College, Kavarapettai. So, classification of magnetic materials. Magnetic materials is basically classified into five types. Okay, diamagnetic, paramagnetic, ferromagnetic. Actually speaking, these are the basic three classification. The remaining two are the extensions of ferromagnetic material, that is ferrimagnetic and antiferromagnetic material. So you would have learned up to in schooling itself the basic three materials, that is diamagnetic, paramagnetic and ferromagnetic. So in a diamagnetic material, the electron orbits are more or less random and mostly all the magnetic moments are cancelled. Similarly, all the spin moments are paired, almost paired. That is, they have even number of electrons and has equal number of electrons spinning in two opposite directions. So what will happen because of it? The net magnetic moment in the diamagnetic material is zero. So that is the major distinction. Okay, net magnetic moment in the diamagnetic material is zero. Therefore, most of these materials do not have magnetism in the absence of magnetic field. So only when you apply magnetic field, you will be able to see the magnetic behavior of the material. Otherwise, we won't be able to see. So that is the significance of diamagnetic material. Now coming to the paramagnetic material. Now when I am talking the next classification, I have to take both together, that is paramagnetic and ferromagnetic. So in these two, there will be net diamagnetic moment in the absence of magnetic field also, which means even if I am not applying any magnetic field to it, it will show the magnetic behavior. That is the speciality of these two materials. Now you can ask, when both are showing, then why two different names as paramagnetic and ferromagnetic? The answer is very simple. One is little weak, the other one is very strong. Paramagnetic is little weak and ferromagnetic is very strong. So in the case of paramagnetic material, this spins in two opposite directions will not be equal. Okay, these spins are not equal. Then there exists some unpaired electrons which gives rise to spin magnetic moment, and hence the resultant magnetic moment will not be equal to zero. However, in the absence of external field, the magnetic moments are oriented randomly. So due to its random orientation, some magnetic moments they get cancelled, and the material possesses very less magnetization in it. But the point is, it possesses magnetization, whereas diamagnetic do not possess magnetization in the absence of external magnetic field. So there comes the difference between dia and para. Okay, now coming to know about some properties of diamagnetic material. They repel the magnetic lines of force. Then if you talk about the susceptibility, susceptibility will be negative and it is independent of temperature. Then if you talk about permeability, permeability is less than 1. There is no permanent dipole moment, and so they are very weak magnets as far as diamagnetic material is concerned. Example is gold, germanium, silicon, etc. Then coming to paramagnetic, if you talk about the properties, the magnetic lines of force pass through the material. Magnetic susceptibility is positive and is also obeying the Curie-Weiss law. What is Curie-Weiss law? Chi is equal to C by T minus theta, where what are all the terms? C is the Curie constant, T is the temperature, chi is equal to C by T minus theta. Okay, so chi is the susceptibility, C is the Curie constant, T is the absolute temperature, theta is the Curie temperature. Then if you come to talk about permeability, it is always greater than 1 and they possess permanent magnetic dipole moment. Then when the temperature is less than the Curie temperature, this paramagnetic will become diamagnetic material. So the examples to quote: copper sulfate, manganese sulfate, platinum, all these are the examples. Then coming to the ferromagnetic material, in ferromagnetic materials the number of unpaired electrons are more. Most of these spin magnetic moments point in one direction. Hence, even in the absence of external magnetic field, the magnetic moments align themselves parallel to each other. See, if I have to show the example in terms of picture, say the spins are like this, okay? Randomly in all direction, it will be like this. The spins are like this. Like this it will be, okay? Now, if I am applying the magnetic field, if it is the case of paramagnetic material, what will happen means all the spins will try to align along the direction of the applied field, but it will not align perfectly. But every spin will try to orient itself towards the applied field direction. Maybe like this, maybe like this, maybe like this. So some part of the spins are aligning themselves, at least they try to align themselves parallel to the applied magnetic field direction. This is for the case of paramagnetic. But whereas for the case of ferromagnetic, in the beginning it is going to be similar to random arrangement. Then when I am applying magnetic field along this direction, all the spins will align perfectly along the applied field direction, which means this is very, very strong. That is what we say. Okay, very strong magnetic field. Then, and also a small magnetic field is enough so that all are aligned parallelly. Okay, that is the speciality. So it is a very strong magnet. Then to say about its properties, some magnetization is always existing in all these kinds of materials even before the external field is applied. That is the major or very significant property. They have permanent dipole moment, so they act as strong magnets. Then they exhibit magnetization even in the absence of external field. This property is called spontaneous magnetization. Then its susceptibility is positive and also very high. It also obeys this Curie-Weiss law, chi is equal to C by T minus theta. When the temperature is greater than the Curie temperature, ferromagnetic material becomes the paramagnetic material. Then permeability is much greater than 1. If you take the examples, it is nickel, cobalt, ferrous, all these are the examples for ferromagnetic material. Then antiferromagnetic material is exactly opposite. That is, the spins are like this. The alignment will be like this. That is equal magnitude but in opposite direction. Ferrimagnetic means not equal, unequal in magnitude but opposite in direction. So we don't have much about ferrimagnetic and ferromagnetic, antiferromagnetic in our syllabus. Just to introduce, I am just telling this. So this is about the classification. We will see further details in the next slide. Now you can see the types of magnetism, then magnetizing field, then when the magnetic field is not there and when magnetic field is present, then magnetization of the material, how it can be drawn, then susceptibility, then relative permeability, the very important parameters. So if you take the case of diamagnetism, then magnetizing field is absent means you can see how it is without any spins, it is available. Then magnetizing field is present, then the spins are just available in randomly, that is in fact aligned opposite. to the field. Okay, the field is along this direction. You can see the spins aligned opposite. Then magnetization of the material, that is when I draw the curve between M and H, intensity of magnetization and magnetic field intensity. You can see a negative slope there. So the susceptibility is negative. So chi is equal to M by H. So when the curve is having a negative slope, automatically the susceptibility is negative. Then relative permeability is less than 1. Then coming to paramagnetism, you can see in the absence of magnetic field, it will be randomly in any direction. Then when I am applying the magnetic field, then what happens? This is trying to align along the applied field direction. It may not be perfect in alignment, but still it tries. Then when I plot a graph between M and H, it is showing a positive slope. So, but it is not very great, which means that you see, if the curve is like this, then it is high value. If the curve is towards x-axis, then it is a small value, though it is positive. So susceptibility is small and positive. Then relative permeability is greater than unity. Then coming to ferromagnetism, in the absence of a magnetic field, you can see the random arrangement of magnetic spins, but still you can see net magnetic moment is not equal to 0. Okay, then when I am applying the magnetic field, then what happens? You see perfect alignment along the applied field direction takes place. Then if I am plotting a graph between magnetization and H, I can see a very great increase in the value, and also it stays stably. So positive and large. You can see this is more towards x-axis, this is more towards y-axis, which means larger value. So both are positive, but this is small value, this is larger value. Then permeability is very large. So this is another picture, another table showing all the 5. Previously I showed only dia, para and ferro, and it includes here the anti-ferromagnetic as well as ferrimagnetic materials. Say magnetic susceptibility is negative and small. Some examples are given here. Then the intensity of magnetization and H is shown, and it is shown that it is temperature dependence, that is it is diamagnetic is temperature independent. Then examples are the shells of the atoms are closed, as in the case of covalent solids such as germanium, silicon, and metals such as copper, silver and gold. Then paramagnetic, it is positive and small. You can see random distribution of spins before the field is applied. Once the field is applied, it tries to align themselves along the applied field direction, and so what happens? The slope, you can see M and H, the slope is positive but smaller value. It is temperature independent. Atoms have randomly oriented magnetic moments, as in alkali and transition metals. Atoms constituting the material having a permanent magnetic moment, as in the case of ferromagnetic material. Then it follows Curie-Weiss law, chi is equal to C by T minus theta. Then ferromagnetic material, the susceptibility is positive and large. You can see a very perfect arrangement of spins. So the value is very high and stable. So atoms have parallel aligned magnetic moments. So the atoms have parallel aligned magnetic moments, possesses large permanent magnetization even without external magnetic field, as in the case of some transition materials or rare earth materials such as iron, cobalt, nickel, etc. Then antiferromagnetic material, it is positive and small. You can see how the curve is between M and H. So antiferromagnetic materials below the mean temperature and above it is paramagnetic. Then ferrimagnetic material, it is positive and large. You can see it is positive and large. Then ferrimagnetic material below Curie temperature and paramagnetic above it. So this is the classification of all the 5 materials with their properties. So note down all the points. You have to write giving the examples, values, everything. Okay. So classification of magnetic materials is done in this video. Thank you, students.